Okay, and our last speaker of morning session is Zhang, who will speak about Newhouse phenomenon in the complex Hénon family. Please.
Thank you very much for the invitation and the opportunity to speak here. Okay, so let me first explain what is a Newhouse phenomenon. But before that, to start, let's review something. It doesn't work. Okay, so we begin with this so-called axiom A maps and axiom A diffuse. So what is an axiom A diffeomorphism? It is a diffeomorphism with a wandering set, which is hyperbolic and compact, and also the set of periodic points is dense in this wandering set. For interval diffeomorphism, interval maps, we can also define this axiom A maps to be the map with finitely many hyperbolic periodic attractors. So each point is a periodic attracting point, and also we can define the basin of these points. The union of the basin, denoted by BF here, is open and dense. Also, we have a similar notion for polynomial maps. We define the hyperbolic polynomial maps to be the maps so that every critical orbit converts to a periodic attracting cycle, meaning attracting periodic points. Attracting periodic orbit, sorry. Okay, so it is known that axiom A diffeomorphism maps, they are structurally stable on the non-wandering sets. In the world of one-dimensional dynamics, axiom A maps are expected to be dense. There are several well-known conjectures. Okay, so first of all, there's this Fatou's conjecture. It said that a hyperbolic map should form an open dense subset in the quadratic family. By quadratic family, we mean the quadratic polynomials as parameterized after a natural change of coordinate by one complex variable C. Also, we have this Smell's question: is one-dimensional dynamics generally hyperbolic? And there are answers. So for real quadratic family, there's this work by Grachik and Zhiyuan, and both of them are Polish mathematicians, I believe, and also independently by Lyubich. In the general case for real interval maps, so this question is finally solved by Klopsky, Shen, and Van Schuen. Okay, so having this said, we now move to the, okay, so this beautiful picture is so-called a Mandelbrot set. You can see this, the set of black parts is the part for which the set of parameters C, for which the critical orbits remain bounded. And you can see on the boundary of these sets, you have a lot of self-similarity and fractal structure. Okay, so, but for highly dimensional dynamics, axiom A maps are known not to be dense. So this discovery is made by Newhouse around 1970. So in fact, the main mechanism, there's a lot of work after Newhouse. So now it is understood that at least for real diffeomorphisms, I mean, for surface diffeomorphisms, it is known that you can have a C omega surface diffeomorphism with a stable holomorphic tangency. And you can even find it within the so-called real Hénon family. So what is a real Hénon family? So given A, B, these two real parameters with B non-zero, you can define a polynomial homomorphism of R2 by the following formula. And for this, you can find basically parameters where you have basically some portion of lamination by unstable manifold. Also stable manifold, stable lamination. So that, okay, somewhere here you have a quadratic tangency. And also if you perturb the dynamic, you don't even need to perturb within this family, this tangency will remain. I don't mean the immediate tangency formed by two leaves we find at first, but because you have a lamination of things, so maybe this immediate tangency will break if you move, but then some other tangency will appear. So this is called a stable holomorphic homoclinic tangency. Okay, so there's a consequence of this. It's not the immediate consequence, but it comes naturally from the proof. So any non-degenerate unfolding of a quadratic homoclinic tangency with of a real surface map produce a parameter with a stable homoclinic tangency. So by that I mean you have a like this. So this is a homoclinic tangency. By unfolding, I mean that if you can change the parameters so that after you change it, you come here. And you have a family of changing of parameters. You require some smoothness for the changing of parameters. Then from here to here, somewhere in between, you find the parameter where you have a horseshoe appear in this region. And with this stable homoclinic. Okay, so this is what we can say for the real maps. Okay, so this is a picture in the paper by Morella and Yokos. So you can see these red curves. They are stable lamination, leaves in stable lamination, and the blue curves, they are leaves in unstable lamination. Okay, now we're going to talk about the complex Hénon family. So complex Hénon family it is obtained by complexifying the parameters in the real Hénon family. So it takes this form. So in our main results is the following. So in a work in progress, we have obtained the following results. This is a joint work with Avila and Avila and Lyubich. So we can show the following. So there exists a parameter B0 bigger than 0, so that any non-zero B with modulus smaller than B0. So there exists a parameter A, so that this complex Hénon map FAB, it has a stable homoclinic tangency. So in general, we need to choose this B0 to be very small. So consequence is the following. So any analytic unfolding of a quadratic homoclinic tangency of a dissipative Sandel periodic point of a map in C2 possesses a parameter with a stable homoclinic tangency. So by that I mean this picture, if you have this picture and if you ask the determinant of this, the Jacobian at this point is not 1. I mean, because we're talking like the modular of the Jacobian is not 1, because you're in a complex world. So in this case, for instance, if you have this, then by doing the same thing, but you consider analytic unfolding, then you can find the parameter when you move from this to this, and somewhere in between you find such picture appear somewhere. Okay, so let me review some previous progress on related problem. So first of all, for the real maps, the emergence of a stable homoclineancy from folding and dissipative on central period points and its various consequences are established in a series of work by Newhouse, Mora, Vienna, and Palis Takens, Palis Vienna, etc. And but in the conservative setting, it's first proved by Durat. I believe there are many other words related to this. And stable homotangency is related to stable intersection between dynamical contour sets. There's a conjecture in this direction about how in the generic situation, dimension bounds imply is the optimal dimension bounds implies the stable intersection. So this is finally solved by Morella and Yokos. So for complex maps, so Buzat has proved this the existence of a stable homotangency exists for some polynomial automorphisms of C2 with a very high degree. So basically, in his case, he need to go from the real world to the complex world, and then need to do some approximation. So usually, the degree of this thing is not explicit and very high, probably. And more recently, Biblier has shown the existence of a degree 2 polynomial automorphism, but in C3, you can have a stable homotangency. And Arajo, Morella, Zamudio, they have proved this open dense subset of pairs of a dynamically defined conformal contour sets with some of the, among within the family of this conformal contour sets with dimension, sum of the dimension bigger than 2. And the sum set has non-empty interior. Okay, so now I want to discuss a bit about the proof, but maybe very briefly. So first we review some basics on this. So this part is very much in analog with the way how these people, the first set of people, they prove these statements for real maps. So the goal is to go from this stable homotangency to the stable intersection between conformal contour sets. So we will find a post-critical finite point, finite parameter A0. So this is called the Mizurevich parameter. So I believe Mizurevich is also a very successful Polish mathematician. Okay, so what does it mean? It means that there exists P0P, so that FA0, P0, 0 is the critical point of the quadratic map. So this point is periodic of period P, and it is repelling. It's a repelling periodic point. Okay, in this case, and also we fix periodic fixed points x at z0 somewhere. So the picture is the following. So maybe let me first draw a picture of the complex Hénon map. You will map this thing in C2 to something like this. Okay. Okay. So when B is 0, the picture is much simpler. It will be just this. So B is not 0, then we are mapping a vertical line to a horizontal line. And when B is 0, you just map each vertical line to some point somewhere. Okay. So by Lyubich parameter, we mean that we mean the following. And think of this thing is periodic. If you map these points, I mean it's going to collapse this curve to some point here, maybe. And there may be some point here. Let's suppose that it come back. So it's this is so A0 corresponding to this situation is called the Lyubich parameter. So in that case, you can define. So in that case, you can see this post-critical point. We have said that it is a repelling periodic orbit. So imagine that if you consider non-zero B, but B very small, then these 2 points are going to lift to C2 and give you a periodic orbit in C2, but with stable manifolds through them, and also unstable manifolds. More generally, if you have if you replace this by hyperbolic sets of the map, you can also do this continuous lifting. Okay, so this is what I said by this rise to a horseshoe for hyperbolic sets, and you can this takes place. So we're going to be interested in the stable lamination through this point. So there's no stable lamination at this point. It's just 2 stable manifolds. But in another place, we can imagine there's a periodic point. Maybe write it like this. There's a fixed point for the degenerated Hénon map. But in that case, you can consider what happens when B equals to 0. When B equals 0, you are in the C, the map A, C, you have a point Z0 here, a map a neighborhood of Z0 to itself. And you take another inverse branch because here, you can also map here by some iterate of A0, some iterate, maybe N2, maybe this is N1. Okay. So this give you a complex, give you a conformal IFS. If you take 2 inverse branches, that give you this. Then if you iterate these branches, in the limit, you find the hyperbolic set. And this hyperbolic set is going to lift for non-zero B, but with B close to 0. Then I will just explain it by picture. So we have this picture, you see. So in the right-hand side, I was drawing these 2 branches. And if you lift it up, then on this lifted horseshoe, you have an unstable lamination. So on the right-hand side, you have this cycle, repellent cycle lift up to have to give you a this red curve, which is the curve I drew here. It is the stable manifold. And by adjusting the parameter perturbing A, you can let one of the unstable manifolds on the left to be tangent to one of the stable manifolds on the right. Right, this blue curve will be tangent to the right curve. It is known that such a tangency will exist. The point is that this horseshoe is here. This you see this thing that looks like a panda bear or something. Then you have 2 branches that give you this, right? And if you iterate them to any order you want in the limits, you find the part of not the invariant of F, but the invariant from iterate of F. So, I mean, on these sets, you know that derivative is going to grow exponentially if you iterate, right? If you iterate forward. in the picture, right part for this part. For now, there's no horseshoe yet. Yeah, yes, that is the the tangency, you can find it, but it's the tangency from one leaf of the blue horseshoe, let's say, to one leaf on this not a horseshoe but a acrylic type. The next thing you do is you have to unfold it. By moving parameter A, you can unfold this tangent. And you can do the so-called homoclinic renormalization that I'm going to explain now. So there's this homoclinic renormalization, meaning that I will just explain by picture. So you can unfold this. So at first it's this, right? And then you unfold it. Okay, it becomes something like this. You can choose it very carefully, a box maybe around here, so that under many iterates, this box will come back to a neighborhood, and in this return map, you can perform a change of coordinates to make this return map look as much as you like to the complex Hénon map. It's degenerated complex Hénon map. So this is the picture. A good thing about that is that you can, by letting the period grow, you can make this. You can make a very arbitrary choice of what the result of the renormalization. It's like before you choosing that, you have this A0, right? You have a tangency, you have A0, but if you perturb it, the return map, you can choose it to be basically any A you want. I mean, in a large region, by only performing a very small perturbation on the original A0. There's a expanding change of parameters from this A0 plane to this A tilde plane. So that is the picture. So, but for this FA tilde, you can consider the same thing again. But in this case, you're going to be very close to the degenerated Hénon map. It's not just that A is unrelated to the smallest of A0, but even smaller. It's related to the period of your dual renormalization is M. By letting M to be big, you become very close to the general picture of FA tilde, right? You can choose FA tilde with a lot of flexibility to have a very thick horseshoe. I mean, a thick horseshoe with a very with a thick stable lamination through it, right? What's that? It is the complex Hénon family. So this is a small f. Is a quadratic family. Quadratic. Yes, yes. It's a quadratic family. Yeah. Okay. So yes, this is a good question. So in all of the rest of the discussion, we will have something a map in the quadratic family. Okay. So let me summarize our goal. Our goal is to do this so that this this blue lamination will intersect or will be tangent to this red lamination, and you want to choose parameters so that the tangency is stable. Okay, so what is the projection? Yeah, projective family. Yeah. Projective family. Yeah. Yeah, projective family. Okay, so the only question remains is how to choose this blue lamination and the red lamination and for them to intersect stably. You can see there's not much flexibility in choosing this blue lamination, but there's a lot of flexibility in choosing this red lamination. So this is the situation we're facing. So I will say two conditions about them. So in the end, the question comes down to, so this part is also well known, comes down to intersection between two conformal contour sets. So it's like I have taken this picture and drew something by myself. So you see there is a disk D, is an orange disk. It's a complex curve. It's a complex disk. But I just represented it by a segment. So this thing is going to intersect both lamination like this, and at the point of intersection, then you see this blue lamination will project to this orange disk. It's called a disk of tangency. It's going to give you a conformal contour set. I mean, just a contour set formed by the limit of a conformal iterated function system. And also you can say the same thing for the red lamination. And in this way, you have you obtain two different conformal IFS, and in the limit you have two conformal contour sets. In their intersection, you find the tangents. So the question is, so this part is also well known. So this reduced to finding two conditions on conformal contour sets so that you have a stable intersection. So let me state the conformal iterated function system. It involved the definition. It's not very important. So you can just think of them as two iterative function system formed by taking contracting maps, contracting conformal maps. The limit set will be represented by lambda. So about this, the intersection of this blue lamination with the orange line will satisfy the following property called a Fourier decay. So we say that this IFS have Fourier decay if there's a probability measure supporting on the limit contour set, so that the Fourier transform of this measure will decay like log xi to the power minus d. And we will not only want it to hold for the original contour set, but also we want it to hold for like the image of this contour set under C1 plus epsilon maps. So this is what we call the dispersive conformal contour sets. So I will spare with you this long definition, but in the end, you can think of it as let's just say the last sentence. This IFS formed by taking this, you map this contour set by a C1 plus epsilon map, and you say the image is also have some decay property, maybe with a different constant. There are examples. So first of all, let's say in what case it cannot happen. For instance, the regular contour set, for regular contour set, it cannot happen. Why? Because for regular contour set, you have a lot of periodicity. Then it's like if you take the Fourier transform, then it's going to you're going to see this Fourier coefficient. They're going to repeat for a long time. Not repeat, but it's going to be large from time to time. So in that case, you don't have this decay. So this is really a nonlinear effect. So the important example is provided in the paper by O and Winter. So they can show the following. So if you have a hyperbolic rational map with degree at least 2, and you have a hyperbolic set generated by IFS with strong separation property. So this is not stated in their paper, but we'll see that it will be the corollary of the main estimate they have. if it is not in the C1 curve, then this satisfies the decay property, or it being dispersive property. In the end, we'll show that this stable contour sets will have this dispersive property for some large integer d and some constant c. And now we're going to talk about the property that we want for this for the contour sets formed by red lamination and orange curve. So this corresponds to this. So we can think of this stable lamination live in a contour set that is denoted by lambda u. It will live here, and then we also want some property for this. So now we have a lot of freedom in choosing this contour sets, but remember we still need to choose it within the one parameter family. I mean, within the quadratic family. So we'll want it to satisfy the so-called lattice conformal contour set. So this is just the name. The important thing is the following. So what we will want is that the contour set is formed in the following way. You can think of this as a disk, the unit disk. Then there's a branch mapping this unit disk to a small disk, a small region. So the map from here to here. Then all the other branches is formed by first you translate this thing. It's really a translation. It's not even approximated translation. It's really a translation. And then first you translate and you map. I mean, sorry, it's the other way. So first you translate and then you apply this thing. For all the others, the same. First you translate and you map. And also you do the other direction, translate and you map using the same branch. And then we want some, this is summarized here. We want some bounds on the derivative, and also we want some bounds on the limit chart. So this will be a result of the some C2 bounds of this. So in the end, this is formed this way. So you're going to have first contraction and then a translation. The inverse branch will be the thing I just said. So where to find this step? So in the end, we're going to find it with this A tilde very close to 1/4. So in that region, you have the so-called elephant's alley. So why this is called elephant's alley? Because you can see this picture looks like a sequence of elephants that walk towards some place. Okay, so there's study of the Julia sets for parameter in this region. So it's done by Shishikura in 1990, even before that, 1994. So for this C, that's very close to 1/4. The rightmost picture, the third picture corresponds to part of the Julia set. You see, this Julia set, it has a spiral round, right, around the neutral fixed points. And also, you have a lot of this translation along. You have essentially translation along two directions. So in the end, you can make a change of coordinates to show that there's a part of the Julia set that is generated by the lattice conformal set. Okay, so I will say very shortly about the main lemma in the one of the main lemma in the proof is the following. So, well, this is not very intuitive, but let's just think about this BMP as one of the domain of the lattice conformal contour set, and this A as the stable conformal contour set, satisfying the decay property. Now the things we are going to do is that we put a dilated copy of this conformal Cantor set with Fourier decay. You want it to overlap with many branch of the lattice Cantor set. So you can draw it like this. There are approximately n translations in this direction and n translation in the horizontal direction. And you want to put a Fourier Cantor set of a Cantor set with some Fourier decay here, right? So I don't know how to write Cantor set. Maybe like this. This looks like a part of the Cantor set. Then you want to show that as long as you put this Cantor set, this purple Cantor set not very far from the middle, then you can find a branch, like this branch. If you dilate this picture here, the same thing appear. Oh, maybe. You have this again, but then this little copy of the Fourier set will appear here. Also in the middle. Then you can consider applying this lemma again. You find another copy. Another copy of the lattice Cantor set, another small copy of the this dispersive Cantor set, and you can apply infinitely many times. And in the limit, you find the intersection. Okay, so I will skip the proof of the lemma, but the picture will look like this. The blue Cantor set will look like these stars, and the red Cantor set will look like this lattice Cantor. You can find a place where, in which place after some dilation, you find a similar picture. Okay. So the main difficulty is on the technical level, it would be to show the Fourier decay. You can really find the Cantor set of Fourier decay. One of the challenges is that if we want to control very directly the branches, we could have some trouble. The reason is that we are going to consider a region where B is very small. So it corresponds to the following thing. It will correspond to like, okay, when you project down in this direction, it will look like this, right? But this is unfortunately is not the Cantor set that we're going to consider. The thing we're going to consider takes place here. So, for instance, if you consider the Hausdorff dimension of this Cantor set, it's related to B. It will be about like I don't know, Hausdorff dimension. Maybe this. Sorry. Anyway, it will be small in B. As B goes to 0, this thing will go to 0. So what we are really looking at is really some Cantor set formed by first of all, not many branches, 2 branches, but each branch corresponds to a very strong contraction related to a contraction of this Hénon map. And also, due to the smallness of B, this map is not even C2. It will be C1 plus epsilon with some very small epsilon. So you have to prove the Fourier decay for this IFS, which is not very regular. there is some literature in this direction. So for the Fourier decay of with a stationary measure, with a sequence of works here mentioned here, and but it appears that all of them require the IFS to be of class at least C2. So this produces some difficulty, and but on the other hand, there are some general part of the method that works. So in the end, you come down to consider so-called derivative cocycle on the limit Cantor set defined like this. You have a conformal Cantor set means that on the horseshoe, the map has a complex derivative, and the complex derivative has two components. One is the R component, one is the R modulo Z component. So if you consider this cocycle, you want this cocycle to mix quickly. There's some non-randomness produced by nonlinearity. So to show this, it comes down to, in the end, the Dogopier's estimate like this for this cocycle, but for in a somewhat uniform fashion for all traces of twisting for the R component and the T component. So I don't have a lot of time, but let me just say that to verify this, the estimate for Dogopier's condition usually require you to have a C2 condition on the IFS. C2 condition on IFS correspond to C1, the differentiability of the cocycle, which we don't have. So we need to deal with this. So, but if we forget about this difficulty, then if you consider C3 conformal IFS, you're going to have Dogopier's estimate as long as we satisfy two conditions for the non-local integrability condition and non-concentration condition. So this can be verified in this example that I have mentioned. Okay, so we cannot verify directly. So what do we do? So this is the technical difficulty I've mentioned. But to overcome this difficulty, we can lift this cocycle to a smooth cocycle on the horseshoe, and when we project it to on the other direction. So just look at this diagram. You have the two projections, right? But this is only on the topological level. There's no dynamic on it. But if you look at the right projection, you will commute with the dynamic on the base and some dynamic on the top. But if you reverse the dynamic on the top, then it's going to commute with another IFS with better regularity. And so what we do is that in the end, we can translate the information we get by projecting on this direction to the somewhat weakened Dogopier's limits on the real cocycle we want. Okay. So I think my time is up. So this is the main this is the solution for the issue. Okay, thank you. Dziękuję.
Dziękuję bardzo. Thank you very much. So, are there any questions? Comments? Talk? If not, then let us thank our speaker again. And let me remind you that 10 to 1 p.m. we have a conference photo in front of the palace. Please